My name is Rebecca Nunu, and I am a research scientist at Southwest Research Institute, which is located in San Antonio, Texas. And I'm presenting some work that I've been doing over the last few years for both my research at work, as well as what was the basis for my master's thesis at the University of Texas at San Antonio. And so the title of my talk is The Application of a Geochemical Framework to Characterize Complex Aquifer Recharge-Discharge Relations in Semi-Arid West Texas. So increasing water demands and limited supplies present severe challenges to many parts of the world. And so taking a long-range look at our water supply is important now more than ever. Pictured here is the U.S. drought monitor from our most recent drought in 2011. And as you can see, or as illustrated, it was quite severe in Texas. And some say it was the worst drought that Texas experienced since 1895. And 12 of the 15 fastest growing cities in the United States are in semi-arid or arid regions, which includes Texas. So our U.S. population is growing in areas that are already considered water stressed. So we can conserve water, we can efficiently use water, but what's most important is that we effectively manage our water. And how do we do that? We understand our hydrologic system so that we can assess how changes in pumping or land use might affect our water resources. And there are a number of tools that we can use when we are managing our water resources. We can do potentiometric surface mapping, we can take water levels, we can do dye tracer tests, and we can also use geochemistry. And geochemistry is a powerful tool because you can highlight very subtle differences in flow regimes, which can be really helpful when you're evaluating spring flow during a drought or during other periods of time. So, in the context of this study, a geochemical framework is a structured approach that uses geochemical analyses, statistical analyses, and geochemical modeling to identify different groundwater source areas and flow paths to discharge points. And in the context of this study, we're talking about springs. And what's really an integral part of a geochemical framework is the collection of robust data, both over space and time. So we're collecting very robust, extensive suites of data over a broad spatial area over multiple sample collections. So, for example, San Solomon Springs is a multi-outlet spring system located here in Reeves County. And it provides an opportunity to use a geochemical framework to better understand where the springs are coming from. We're located here in Trans-Pecos, Texas. You see, can I use this? There we go. We're located here in Pecos. And here are where the springs are located, along the Jeff Davis-Reeves County border. And so the San Solomon Spring system includes 6 different springs. Phantom Lake, which we've talked about, which is flowing now but hasn't been lately. Giffen and San Solomon, which is Balmorhea State Park, as well as Saragossa, East Sandia, and West Sandia Springs. And collectively, these springs are important because they provide habitats for federally endangered and endemic species and are important to meet irrigation, municipal, different needs to the communities. And so Doc Ward really set us up here for success in highlighting how complex the geologic environment is in our study area. We have multiple aquifers, we have the same rock types, different rock types, structural controls that provide a very complex geologic environment. And consequently, a very complex sort of recharge mechanism to the springs. And so a number of people have established a great conceptual framework for us in understanding flow to the San Solomon Spring system. What's pretty much established now is that there's a regional flow system that originates in the Wild Horse Flat near Van Horn, Texas, and these regional flow paths emanate along in this direction to meet the springs along faults and fractures. There are also local flow paths that have been ascertained to come from the Rustler Aquifer and from the Davis Mountains. And so with all the stressors that I've mentioned and with how complex this geological environment is, it warrants a closer look at where the water is coming from to feed all 6 springs. So, the research objective of the work that we have been doing is to investigate the hydraulic relationships among the individual springs of the San Solomon Spring system using geochemical and multivariate statistical analyses. And in doing so, we hope to apply this geochemical framework to ascertain if different local or regional sources feed the spring system. So the first step in our technical approach is the collection of an expanded suite of geochemical markers. And I won't bore you with the details, but we collect a broad suite of analytes, our major ions, which Doc Ward referred to, minor ions and elements and nutrients. We look at a broad range, a multi-isotope approach, and we also collect data in the field so that we know what pH, temperature, DO, all of those in situ parameters are while we're collecting our samples. And so I thought I would just include a few photos from our field campaign where we've collected from all 6 springs multiple times, thanks to the help of a number of people, including Greg. Here's Phantom Lake, Giffen, Saragossa, East Sandia, San Solomon, and West Sandia. So once we've collected this robust suite of data, we send it to the lab, and a couple months later, we get all of these data that we have to interpret and make sense of. And in doing so, we use geochemical and multivariate stats to make better sense of what the chemistry tell us. So we may look first at our major ion composition. Pictured here, which we saw previously, is a Piper diagram. And a Piper diagram is just an easy first stab at visualizing your ionic data. And as you can see, there's not much separation amongst these samples. We sampled from an Edwards well, a Pecos well, another one from the volcanics in the Davis Mountains, as well as all 6 springs. So again, there's not much separation. Ron? Thanks. Not much separation that we can see here, although there are a few samples that stand out. Saragossa Spring, as well as our sample from the Davis Mountains, which are markedly different from the rest of our samples. If we take another look at our data, here's a box plot, which is essentially all the data I have on each of the springs for sulfate, which is a major ion. And there are some distinct clusters that we can notice right away. First, we see that Giffen, Phantom Lake, and San Solomon measure about the same, as do West Sandia and East Sandia springs. And again, Saragossa kind of does its own thing. And so as I proceed through these images or these figures, I want you to pay attention to how we consistently see groupings of data or groupings of the springs in our data. So multivariate statistical analyses, I won't bore you with the details, but it's essentially a way to reduce hundreds of variables, if you want, into a smaller number of components so that you can understand which components provide insight into the most variability of your data. Let me show you. So here we employed factor analysis, and this is sort of a visual product of that statistical method. But here we see that 80% of the data is accounted for by this statistical method. And again, we see these groupings. Giffen, Phantom Lake, and San Solomon have similar chemistry. West Sandia, East Sandia as well, as does Saragossa. And see, we couldn't see this before in our Piper diagram, and as we've applied more geochemical analyses, we're able to better refine what the data are telling us. There are also a few other data points that stand out to me. There's a subset of Giffen, Phantom Lake, and San Solomon, as well as East Sandia Spring. And so what's not obvious by this figure, but what I can tell you about the data, is that these subsets come from two sampling events that happened after rain events. So in 1990 and 2004, there was significant rain, and these sample points show a different signal in the chemistry related to the rain. For Giffen, Phantom Lake, and San Solomon, this is characterized by fresher water, which would make sense, whereas East Sandia is characterized by higher TDS or more constituents being shown up in the water. So we can also use isotopes. Isotopes are kind of a way to know what the fingerprint is like in a particular water, where it's traveled, what the age might be. And if we go forward, we might start off with isotopes of water, which are deuterium, which is an isotope of hydrogen, and oxygen-18. We may use a reference standard, which is the global meteoric water line, which describes the average relationship of these two isotopes in natural waters. And the USGS came out with a report a couple years ago that established a threshold for how these isotopes might plot along the global meteoric water line in our study area. Here's oxygen-18, and if our values are greater than negative 7.5 per mil, it's indicative of local recharge, think rainwater, whereas less than is likely submodern recharge. So waters that are coming from the Pleistocene, or very old waters coming from the northwest. And so here we have our Saragossa sample that is, again, doing its own thing, whereas the rest of the samples plot quite nicely as exhibiting a submodern recharge signal. We might also use carbon isotopes. Those are commonly used in these sorts of water resource assessments. And here we have carbon-14, which can be used to tell you the age of the water. Carbon-13 cannot, but it can still tell you about the different flow paths in which water has gone through, interactions with the soil. But what I want you to take away from this is, as carbon-14 decreases, carbon-13 increases or becomes more enriched. And that's because as the water flows through the system, it gets older and it interacts more with the matrix. So we would expect that we see this inverse relationship. And everything fits quite nicely for the most part. As all of them plot along this line, we can say that they are likely all a part of the main flow system. But there is this deviation of East Sandia, West Sandia, and the Pecos alluvium that doesn't plot quite where we might expect. We might expect it to be a little bit more enriched in carbon-13 or have a lower carbon-14 signal. And so what I take away from this is there is likely some input into the system of fresher water that is diluting the signal at these two springs. Here again we have our same cluster of Giffen, Phantom Lake, and San Solomon. And we also see the 2004 and 1990 signal in which our values are diluted by rainwater. And then again, Ron, Saragossa exhibits what we might expect from rainwater. So a very modern signal, which is what we have consistently seen in our other plots. So these aren't all the analyses I've done. There are a number of other things that have guided our interpretations. But once we finish our geochemical analyses and our statistical methods, we can come to a refined understanding or conceptualization of a hydrologic system. So there are a number of clues that we have that a larger regional flow system is feeding this spring system, namely isotopic compositions, which are consistent with older groundwater that was already established by previous authors. Again, remember this submodern recharge plot that I showed you, which is shown up in all of the springs except Saragossa. And here again is that flow path that I mentioned, to where all of these regional flow paths are meeting the springs. So that's one recharge source that we would characterize as regional. We might also use our elevated ion concentrations in the sandias, as well as our carbon isotopes, to indicate that there is some mixing of water. Maybe it's rainwater, or maybe it's something like irrigation return flow, where you take older waters that already have an older signal and re-add it to the system. So you're recirculating these waters, so it affects the signal in the sandias, but yeah. So what we suggest is that there may be a local recharge component that is added locally via irrigation return flow or some other sort of input into the system. So consistently we saw that Saragossa Spring kind of does its own thing, and what we suggest is it is likely a seepage spring that is more heavily influenced by a near-surface component. Again, doing its own thing consistently, both in the isotopes and the ions. And lastly, a subset of the records for San Solomon, Phantom Lake, and Giffen indicate that there is some other sort of local flow component that occurs and provides recharge to these springs. I can't say for certain how the other springs might be impacted, like East Sandia. I mean, clearly East Sandia has a different response, but I don't know what West Sandia or Saragossa would exhibit after a rain event. But there is some local recharge input via rain events that is occurring and feeding the springs. And so here we are situated in Balmorhea. There was a study that came out a couple years ago that said that these outcrops, these Edwards outcrops that are in Culberson and Reeves County, are likely the location of how rainwater enters the system and feeds the springs. So, what's next? We've done quite a few sampling campaigns, and we're really glad to say that we're going to continue our work in the area for the next 2 years. We recently received a Bureau of Reclamation WaterSmart grant, in which we will continue our geochemical sampling and application of a geochemical framework so that we can sample more, both over time and over a broader spatial area. This work wouldn't have been possible without our collaborators. Special shout out to the Reeves County Groundwater Conservation District, the Middle Pecos Groundwater Conservation District, the Nature Conservancy, the Horizon Foundation, and the Environmental Defense Fund.